coming. My name's Julian Hyde. I've dabbled in a few different areas over the years, a lot of it in open source. I guess I'm most known for SQL query planning, but I was chief architect of a company called SQL Stream a few years back, which combined SQL and streaming. So I'm still pursuing that passion here. I'm an Apache member, and I was the original developer of Apache Calcite. I'm still very active in that project. Also a member of some other Apache projects like Drill and Eagle and Kylin. So why SQL? Why choose this particular language? And everyone who doesn't like SQL or isn't familiar with it knows that it's been around for 40 years, and it's a database language, right? So why are we applying it to streams? I think the biggest point is that it's all data. Whether it's data at rest or data in motion, it's all data. And data is valuable. And recent data, the kind of data that exists in streams, is even more valuable in a lot of cases. So enterprises want to see all of their data, and they don't want to have to switch programming languages or switch paradigms to read the data that happens to be in Kafka right now, as opposed to data which happens to be in HDFS. So SQL is potentially a unifying language to allow you to get at all of the data and allows you to interoperate. There's also this thing called stream database duality, which is you can look at a database as kind of the sum total of all the data that's flowed into it via streams or ETL jobs or whatever. And you can look at a stream as kind of the deltas to a database. So really, there's the same content in a stream. You could view a database as simply a cache of everything that's flowed through the stream. So there's the same content in both of them. If we're looking at data languages, SQL is, I would say without question, the best language ever invented for doing data. Because it's got this property that it's declarative, a property that very, very few other languages have, which is you say what you want, and then the system, there's always an optimizer involved in the SQL system. The optimizer figures out how to get that, and that may mean radically changing how the query is structured in order to get the right answer in an efficient way. And underpinning that, SQL is very well founded mathematically, and that's necessary for the optimizer to be able to safely transform these programs in radical ways. And the big surprise is that a lot of the operations, or all of the operations you would do on data in a database, the relational algebra, they make sense on streams. So, let's see what happens if we put SQL on streams, and let's see how useful it turns out to be. So the reason I'm involved in this is I'm not a committer on Apex. I'm a contributor, and I've worked with the community. What I'm trying to achieve, and what the Calcite project is trying to facilitate, is creating kind of a standard or a consensus about what streaming SQL ought to look like. We definitely don't want a SQL-like language, because the SQL, there's a lot of different ways you can do SQL-like languages that don't deliver all of the benefits of SQL. Calcite is providing the leadership and working with several Apache projects and other groups as well, just figuring out what this streaming SQL should look like. And we are, trying to stay within the spirit of the existing SQL standard that's used for databases, but hopefully, in a few years' time, we'll be looking at streaming extensions to the SQL standard. So in Calcite, we provide a parser for streaming SQL and a validator and kind of the beginnings of an implementation of it. Apex uses that. Flink uses it as well. Storm uses it. So the idea is to make it easier to implement the streaming SQL. But really, any project is free to implement their own implementation of streaming SQL. They don't have to use our software. So streaming SQL support was just added in Apex. It's part of the Malhar library. I'm going to be talking about, and this is a slide from a blog post in January about that support. As you can see, we use a SQL statement at the top. We translate it down to relational operations, and then that is translated into Malhar operations. So this is a pretty typical pattern. I'm going to be talking about a lot of operators and a lot of example SQL statements that aren't supported in Apex right now, and I'm not my goal is to communicate what streaming SQL is capable of, and look at some of the directions that Apex could take it. I understand that on the roadmap is window operators, but I can't really speak for what is going to happen in the Apex project. So some examples. Here are two simple queries. The top one, select from a products table. That's a traditional non-streaming query. Find products whose unit price is less than 20. The bottom one is a streaming query, and orders is a stream. So I'm interested in orders of 1,000 units or larger. The only difference between those two things is the stream keyword. We'll see why that stream keyword has to exist in the next slide. And the reason is, these are two queries, both of them on the orders table, or is it the orders stream? And the interesting thing is, for some purposes, you may be interested in orders as a stream. So tell me immediately if I get an order which is more than 1,000 units. But I might also be interested in all of the orders I've received over the last 5 years. So sometimes you're interested in the deltas, what's changing now, and sometimes you're interested in history. And one of the things that makes streaming SQL powerful is that we can basically use the same object for both. And one of the kind of best illustrations of the power of this is when we have a query where we actually want to combine past and future. So I'm interested in, tell me about all the incoming orders whose order size is, let me see, greater than the average size of orders over the last year. So I actually need to scan. Now, clearly, if you imagine how this query would be physically implemented, we've got an orders stream, which is in Kafka, say, and we've got an orders table, which is in Hive, say. And what we want to do is, from the context of that in the query, we actually want to use, for the top incarnation of orders, we want to read from Kafka. And from the bottom one, we want to read from Hive. Or perhaps for the bottom one, if we're interested in, if orders more than 24 hours old haven't reached Hive yet, maybe for the bottom one, when we're reading from historical orders, we actually want to combine the orders that are still in Kafka that have occurred over the last 24 hours and the last 3 years of data from Hive. I don't really know the answer. The nice thing about the fact that SQL is declarative means the system is going to figure out how to connect all the various different pieces, how it's going to read recent records from Hive, recent records from Kafka, and older records from Hive. The power is that an end user can simply write those 7 lines of SQL, and the system will do the right thing. So, this is why SQL is still around for 40 years later, because you're expressing your problem at a very high level, and the system is figuring out the details. And by the way, a system administrator might decide to change the Kafka partitioning scheme, or decide to, let data reside in Kafka for a bit longer. They can change the definition of the orders table or the orders stream, and you don't have to change the application. It automatically adapts. This is something that people have been doing in SQL systems for years. You'd write your application on your tables. You wouldn't bother to define any indexes, and if the performance was bad, you'd add the indexes later, and you wouldn't have to rewrite your application. This is what it means to say SQL is declarative, and that kind of those values of having a declarative language are very useful for streaming applications. So semantics. I guess you can't have a talk about languages without a slide about semantics. I call this the replay principle. You know, we've got an existing SQL standard. We don't want to have to write, and it's large. It's probably 2,000 pages. We don't want to have to write another 2,000 pages to define what streaming SQL should do. So we have this simple principle that if you execute a streaming query, it produces the same result as if you'd put the data in tables and you'd executed the query on those tables. The output shouldn't, just as in a relational database, the result doesn't rely on how the data is physically ordered within the table. The output of the stream shouldn't depend on the relative order that things arrive on the stream. Now, obviously, when the data comes out will depend on when things arrive in the stream, but the actual result should not depend on that. And so we have to, introduce details like triggering schemes so the system can figure out when when we can emit the total of the number of orders received between 10 a.m. and 11 a.m. We have to know when we have all of the data from 10 a.m. to 11 a.m. And those are some of the details that various streaming systems are working on. But this replay principle at least puts us on fairly solid ground as far as what these queries are supposed to do. And it also has a nice property. If you want to build streaming queries, you can build it on the historical data, run your queries multiple times, get the query right, and then you can switch it over to run on streams. So controlling when data is emitted. So this is, and I should mention that kind of what we're doing in Calcite and streaming SQL is very analogous and complementary to what the folks are doing in Apache Beam, creating an API, a standard API for describing streaming applications. So, and one of the strengths of Beam is a very good model for how to emit data, emit partial results, that kind of stuff. So we're talking about adding this emit keyword to streaming SQL that allows you to define, do you want to accept early emission of results, and then, under what circumstances would you restate results if you get extra data that arrives late? So aggregation, the examples I've showed you previously have a scan, a project, which is the select clause, and a filter operator, which is the where clause. Aggregation is kind of the most interesting and most complex area of stream processing, and there are several different kinds of aggregation that people tend to want to do on streaming data. In SQL, you generally use the group by clause to aggregate data to compute totals. There's also, SQL has grouping sets, which allows you to emit multiple levels of aggregation, so a grand total and subtotals. And then SQL also has an over clause, which allows you to compute things like sliding windows. So the plan is to support all of these in streaming SQL. And let's just show some examples here. So if you're interested in tumbling windows, an example of a tumbling window is every hour emit the total for that hour. A hopping window is similar but slightly different. So every hour emits the total for the last 2 hours, which means that each given record is going to appear in, if a record occurs at 9:30, then it's going to occur, it'll be in the 9 till 11 total, but it'll also be in the 8 till 10 total. And then a session window is where you're looking at events that occur within 1 hour of each other. So a burst of activity will form a session, and then will be grouped together. And then there'll be perhaps a pause in activity, and then another burst of activity. So we're adding constructs to the streaming SQL to support all these kind of windows. And I don't have time to describe sliding windows, but they're also supported. The pie chart problem is kind of deceptively simple. I think it's kind of it's one of the most interesting things that streaming SQL can do. The paradox is people often want to do relational queries to, for example, generate a pie chart in a web page based on a stream. So they don't want streaming output to the query. They want the kind of queries that Tableau generates. They want to do BI on this. But they want BI on incredibly recent data. So if you try and write a streaming query, if you're trying to write a web application, you can't write it on top of a stream because at the precise moment that web page is being generated, there's only one record out of the million records that have flowed over the last hour. So you actually want something to be collecting together that last hour of data. And there's an opportunity here for a streaming system to gather together kind of recent summaries of data so that applications like web pages, like Tableau and so forth, can run on data which is still inside Kafka or inside the streaming systems. Joining is a huge topic, but another thing that streaming SQL makes possible is combining a stream with tables. It's very often only part of the information is in the stream. The extra information is in a table. So in this particular case, we've got an order stream and we want to join to a products table, or basically a price list information. What happens if the products table is changing? That's a complicated issue. Take a look at the Calcite site. We've got some examples and proposals how to solve that. Then lastly, joining a stream to a stream. Orders and shipments. Often there's a time, or almost always there's a time component there. Join orders and shipments which are on the same order ID and occur within 1 hour of each other. A lot of other operations make sense. Even things like subqueries, exists, and in, and so forth. I wanted to draw your attention to the last one, match recognize, which is something that Oracle introduced, and basically allows you to define the kind of patterns that you want to do for complex event processing. So, for example, if you're looking at stocks, 2 upticks followed by a downtick, or in security event monitoring, you might be interested in 3 failed logins followed by a password change, followed by a large withdrawal from a bank account. The match recognize clause can represent those kind of patterns. And we have experimental support in it in Calcite, but it'd be an interesting area to develop. A brief word about what Calcite does. It does planning, and query planning means, and cost-based optimization basically means representing a query. This is not a streaming query, I apologize. This is a relational query. But the basic idea is if you can find ways to transform the query that preserves semantics, then, and in this case, we can push this filter through the join and into the Splunk data set, then the query produces the same results, but it produces it more efficiently. And what Calcite does is a framework for writing these query transformation rules and applying them to your query in a safe way. So that's a one-slide description of Calcite. We work with a lot of Apache projects. We're embedded in a lot of Apache projects and a lot of commercial projects as well. So, and since this is Apache, join the community. The best way to get in touch with us is to join the dev list and just start posting. Start talking to us. And of course, submit pull requests. So thank you very much for your time. I don't think do I have time for any questions? Okay. Are there any questions? Yes.
You show the sort on the last slide, and when you have a streaming query, you keep sorting. If you resort the whole data every time, that would tend to be extremely inefficient versus sorting only the new data.
Yeah, it's not only inefficient, it's impossible.
Yep.
Yeah. Yeah, the common thread in in all these streaming operators is there has to be some time component. If you ask for all orders sorted, you're asking an impossible question. But if you're asking to sort the orders within the last hour, so give me the top 10 orders within the last hour, that is possible for the system to do. Yeah, we need to devise a way of asking for the top 10 orders over the last hour. So we're not trying, streaming SQL cannot make questions which are impossible to answer possible, But if the idea is that legitimate questions that people are asking, and people are perhaps already writing in Apex, if we can find a way of representing them in SQL, then we can find ways of applying the optimizer to them and interoperate with stored data and so forth. Does that make sense?
There's a specific, when you need to sort data and new data comes in, let's say over the last hour. So new data came in, all data is now irrelevant. If you now go and sort all the data of the past hour again versus just taking the deltas and dropping from the sort and inserting new in the sort, that's vastly different mode of operation and vastly different performance metrics. And in SQL, how do you do this? How do you implement this streaming? If you say that it's the same thing, just you operate over an existing table.
Yeah, if you were to say select from orders, order by units descending, Calcite would say, I'm sorry, I can't execute that.
Just the last hour, but streaming. So you keep repeating this every second or minute or whatever, right?
Yeah. So if I was to do that, if I said order by hour, comma, units, it would say, what he's asking me to do is, first of all, order by hour, which is a monotonic column, right? So it's, 9 a.m. on Tuesday, 10 a.m. Tuesday, 11 a.m. Tuesday. And then within that, you're asking to order by the units. So that is something that it can deal with because it knows that every hour it knows that it only needs to sort the last hour of data, and then it can throw the previous data away. If you've got any more questions, I'll speak to you afterwards.
I have a question. This is Subbu from Synerzip. This streaming query, you said that it'll be active from now until plus infinity. So is it true that the query will be active as long as the system is up and running and look for the pattern or the data that it's going to select?
Yeah, that's the idea. Is the query it becomes a standing query and the data flows through it.
And is there a polling that happens for the data, or how is the data fetched from the select query?
How's the query implemented? Probably using a system similar to Apex. I mean, it will be a DAG of operators, which are taking incoming data, processing it in some way, filtering it, putting it in hash tables, whatever. I mean, that kind of, the model that Apex has is pretty much ideal for executing streaming queries.
Okay, so it depends on how you implement the operator to select, and then based on that, it's going to do it in near real time.
And depending on which engine you're using, some engines may not be able to support windowed aggregation. So depending on what engine you're using, the system may say, I can't support that. Okay. But if it's a reasonable thing to ask for, then eventually, hopefully, the engines will support it.
Okay, thank you, Julian.
Okay, time for one more, okay?
Assuming my Windows is in seconds, and I want to compare with the last hour's average. Is this average being calculated for the previous hour? It's kind of incremental calculated, or it's like a calculated whole hour every time?
Are you saying if you want to compute the average over the last hour?
Yes, and because my Windows is in seconds, so when my query, it's going to query for every second, right, to compare with the last 1 hour of average. It is average being calculated incrementally, just deal with the previous history and the current incremental part, or it's calculated every time for the whole hour's data?
How to implement it is a matter for the engine, but this is what the Windows is all about. So sometimes if you want the average of the last hour, you want it on hourly boundaries between 10 and 11, and then between 11 and 12. That's a hopping window or a tumbling window. If you want a sliding window, if I get a stock trade at 10:46, then I want to see the average between 9:46 and 10:46. And if I was implementing an engine, I mean, I did it back in SQL Stream, we definitely maintained we actually had an entry in a hash table which maintained the running total. So every time a trade happened, you know, it would add the data for 1046 and subtract the data from 946. And be careful about underflow and overflow. So that's how I think an engine would implement it, but it's really up to the folks implementing Malar or whatever engine, how they do it.